Okay, so lastly, let's talk about simple proportions. Okay, we have talked about simple means, and we know that simple means has very good properties for us to say the distribution of simple means. Okay, now sometimes we cannot apply simple means, then sometimes simple proportions can help us. For interval or ratio data, or we say quantitative data, we have defined simple means because we can do the calculations, we can do the arithmetic of the average. And we know the distribution of simple means. What if we have ordinal or nominal data? Then things would become more complicated or more difficult because there is no such thing for simple mean. However, we have something called simple proportions to be defined later, and you're going to see that simple proportion can be viewed as a special case of simple mean. And then everything we have from simple mean can be borrowed to ordinal or nominal data. So suppose we are interested in the proportions of girls and boys in NTU. Okay, I want to know it. So let's consider this question. To do some investigation on them, let's label girls as 0 and boys as 1. In that case, we would say xi is a random variable whose values may just be 0 and 1. And I use xi to denote the sex or the gender of student I for I from 1 to capital N. And the capital N would be the total number of students in NTU. Okay? Then we define something called the population proportion of boys as this. We now have labeled all the boys as 1 and the girls as 0. So if we sum them up, that's the total number of boys. If we use this number to be divided by n, that's the proportion of students that are boys. Okay? And we use P to denote this population proportion. If we want to know the population proportion of girls, that would be 1 minus P. Okay? Nothing special. Now, if this is the population, let's consider a sample whose sample size is small n as our sample. And then, again, let's assume that xi and xj are independent. If among these 30,000 or more students, we only select 100 students, that's typically fine. Then the sample proportion is defined in this way. You can see only capital N becomes small n, so we are counting the number of boys in a sample divided by the sample size. Here we denote the number as P hat. P hat. The population proportion P is a fixed number, although we do not know it, but it's a fixed number. On the other hand, the sample proportion P hat is random, right? Just like sample mean. P hat is also random because you don't know how many boys you will get in the next random sample. You don't know whether today's random sample and tomorrow's random sample would be the same or different. So that's why P hat is random. Now, we are interested in the distribution of P hat, okay? Because if we have P hat, then we can use the sample data to infer the population data. Okay, so before we can really give you the theorem, we need to first study something called Bernoulli random variables. Okay, because our random variable x here is very special. It's a binary variable. The sample size is just 0 and 1. Okay, so we need to first have some understanding about this kind of special random variable. That P equals the probability for x to be 1 to be our success probability. And you can see that this P is having the same notation as population proportion, right? This is exactly population proportion. When we have a random variable x, the probability for x to be 1 should be exactly the proportion of x being 1, right? Because you only have two possibilities, 1 and 0. The total values are there, and the sum of them are 1. So if you randomly pick one, the probability for you to get 1 is just the population proportion. In that case, we say capital X follows a Bernoulli distribution with probability P. This probability P decides the shape of your Bernoulli distribution, right? P may be small for this X, P may be large for another Y. Different variables may all follow a Bernoulli distribution, but their success probability may be different. We use this notation X follows Bernoulli with probability P. Okay, now is the important part. We want to calculate the expected value and the standard deviation of our random variable X. Okay, random variable X. Again, we may use the general formula to do that. So let's calculate expected of X, the expected value of X. You know that the expected value of X is, first you take all the values and then you do a weighted average of all these possible values with their probabilities. So here, possible values are 1 and 0, and their probabilities are P and 1 minus P respectively. So if you do this weighted average, you get P at the end, and that's the expected value. When you select one value from this population, the expected value is P. The expected value is P. And once you have it, we may go further to calculate the standard deviation. Okay? Before that, let's calculate the variance because it's easier. So the variance again is that for each possible value, you collect or you calculate the difference between it and the mean. Okay, the difference between it and the mean. Now this P comes from here. This P comes from here. You calculate the deviation, square them, and then use their probabilities to do a weighted average. Okay, once you repeat this, blah 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 blah, you're going to get P times 1 minus P by doing some arithmetics on them. So that means when you try to collect one value, you have some randomness, and the variability is measured with this variance P times 1 minus P. Once you have it, your standard deviation would be just square root of that. Okay? So one thing that is interesting is that when do we have the largest variability? Okay, now think about this. Suppose your P is 1, then your sigma square X would be 0, which makes sense. If all the, for example, for NTU students, if all of them are boys, then there is no randomness. When you select one guy, it must be a boy. If your P is 0, then again, you have no randomness. If all of them are girls, when you select one student, she must be a girl. But what will happen if your P is 1/2? In that case, your variance would be 1/4, right? And you can show that this is the largest possible value. For any other possible value, this number is smaller. For example, if P is 1/3, you would get what? 2/9. If P is 2/3, then it's the same thing. For any other value of P, you cannot beat 1/2. What does that mean? That means if you are going to predict what you will get in a random sample, then the prediction is the hardest, is the most inaccurate if there are exactly half of the students being boys and half of the students being girls. In that case, it's just the hardest to do the prediction, which makes sense. Okay? Okay, so now we're ready to talk about the distribution of the sample proportion. The distribution of the sample proportion. Note that the sample proportion is a special type of sample mean, right? The formula is just sample mean. The only difference is that xi is just binary. Even if xi is binary, still it's a sample mean because it's doing exactly the sample means task. The average, the arithmetic average still has a physical meaning. It's just mentioning the proportion. Okay, so this formula can be used and can be viewed as a special case of sample mean. And that means we may apply the central limit theorem again. I don't care about the population proportion, but as long as n is at least 30, we can say that the sample proportion is approximately normal. And then the mean and the standard deviation would be straightforward. Just p and following this formula, p times 1 minus p divided by n taking square root. Okay? Now, again, these two things has nothing to do with central limit theorem. Central limit theorem simply tells us approximately normal. Okay? This depends on central limit theorem, and this does not. These are true for all population. Oh, so hard. Okay, and these are true for all kinds of population distribution. It does not depend on central limit theorem. Central limit theorem tells you this at least 30, you have approximately normal. So this is useful. And another remark is that when you are talking about this population, you know that the population is 0, 1, right? Your xi is obviously not normal because your xi is Bernoulli. So now you cannot say anything if n is small. But if n is large, then you can say it's normal. Okay, so let's try to apply the idea. According to a survey in 2011, not really, according to the census in 2011, there are around 20,000 boys and around 13,000 girls in NTU. So we can calculate the population proportion of boys as around 60%. So let's try to sample 100 students and find the sample proportion p hat. Obviously, p hat is a random variable, right? We don't know who will be in that 100 students. So we want to know what's the distribution of p hat. And we want to know, for example, what's the probability for us to see fewer boys than girls. Okay? In the population, there are more boys than girls. There are 60% of students that are boys. But still, it is possible for us to get fewer boys than girls in a random sample, right? We use this as an example to show you how to do the calculation when we have those knowledge. So the distribution of p hat is the following. Because n is at least 30, so it's a normal distribution. So we're saying that p hat is normal, okay, according to central limit theorem. And then the mean would be around 60%. And this has nothing to do with central limit theorem. This is the simple fact we get at the very beginning of today's lecture. Okay, so we have around 0.6, and the standard deviation is calculated in this formula. P is 0.6. So let me write it down. P is 0.6 times 0.4 divided by 100 and the square root of it. Okay, you can calculate it as around 0.05, nothing special. So once you have this, you can calculate the probability for boys to be less than girls in your sample. And that means your probability, your p is less than 1/2. And to calculate this, it has nothing different from doing a tail probability for a normal distribution. Okay, something you already know how to do. So a quick summary. A sample proportion can be viewed as a sample mean for qualitative data. Can be viewed as a sample mean of qualitative data. You can do this only if you label the two groups as 0 and 1. Okay? You cannot do this if you label them as 4 and 10, 5 or 0, -2 or 10. You can only label them as 0 and 1, so that the formula for sample mean really gives you sample proportion. Okay, so you can only label them as 0 and 1. Also, this method is limited because if you have more than two groups, more than two categories in this variable, then you cannot label them as 0, 1, 2, 3, 4, 5 and then do sample mean. That's going to give you meaningless outcome. That's not sample proportion. So for sample proportion, you can only label them as 0 and 1, true or false, success or not. For example, you can say, you can define the categories as rolling a dice and getting more than 5 or less than 4, something like that. But you cannot talk about the 6 possible values together. Okay, it's normal when the sample size is large enough. Your sample proportion is a normal random variable when your sample size is larger than 30. And this is the outcome of central limit theorem. Okay, so that's the end of today's lecture. Thank you.